So where would you put these things? You know, you can use them as standalone bandpass filters where people buy them from DigiKey or buy them in bulk. You can use them as other things like oscillators and resonators. These are devices that uses frequency references. So if you need in a certain signal to produce you need a 1 gigahertz carrier to do something. You use an oscillator or a resonator. So an oscillator acts as a voltage reference or a frequency reference. So you can just burst an ENL. You can give it a burst of just a square pulse voltage, and then what comes out of the ENL is the resonant frequency of the ENL. Because that square pulse contains theoretically infinite frequencies, it will only pick out the resonant frequency that it adheres to. So instead of a filter, it becomes a producer of frequencies. So yet another way of using it. I have high hopes for RFID technology because the ENL produces a relatively strong peak easily, and the receiver is, you can use an ENL to produce a signal, you can use an ENL to receive the signal. And because when you're receiving it, essentially ignores all of the noisy environment, we can get a fairly good range. So this was done only theoretically. We haven't built an RFID ENL. But I have some RFIDs sort of prototypes, and they're pretty terrible, you know, to be perfectly honest. I mean, it works here, and then you take a step back and it doesn't work. It doesn't work at all. Like, that's not the range that I would expect, you know, a significant decrease in signal. So we could use them for tagging. They could be customized because you're not looking at custom technology, at standard off-the-shelf technology. You'd order, you know, 1 million ENLs at a certain frequency and only have to tune the transmission line lengths, and now you have your own RFIDs that, you know, if you don't tell people what the length is, then how are they gonna hijack it or stuff like that. So there's a lot of security sort of conversation about what the safety of RFID technology is. Essentially, we're looking at telecommunications and GPS and some RFID applications at 920 megahertz. The rest of them are all telecommunication, Wi-Fi a little bit higher up, around the 2.4 gigahertz and 5 gigahertz for Wi-Fi AC, and GPS is very specific frequency at 1.575. And then get as high up in the terahertz applications as we can. It's just the quarter wave, you have a benefit of half of the transmission line length, so you save some space. This uses a little bit less power, but it's not enough to justify switching from one design to another. But now we're moving in, so we having verified the theory and the technical, and having built the models and having done the prototypes, now we need you know, seasoned professionals or a team of professionals in electronic engineering, where we can run off various prototypes and continue the development in hand. So you know, where would I suggest this goes? I would, again, academically want to compare the quarter wave versus the half wave resonance comparison. Again, this is purely academic, but I don't know what can come out of this academically speaking. We should populate the PCB boards for active feedback mode. This is something that's only been done in the simulations, and this will help us drive what we call delta function response, so very, very high peaks, very, very sharp high peaks that could be used for various other things. The notch filter needs a separate research and development effort, possibly another grant effort or an investment effort for stakeholders who are interested in that specific thing, possibly from the US government or military, where they're looking for jamming equipment and some radar applications. The multiband ENL or ENL bank design, that's an effort that's currently underway with a grant to the National Science Foundation. This is where the ENL really shines. If you have multiple streams, complicated input signal, where you're trying to simultaneously get a lot of information out at the same time, the design of the ENL completely outweighs current bandpass filters because there are no multi-band bandpass filters other than parallel band filters currently out there. It's like the ones that we described. You just have a lot of bandpass filters on your phones and things. I guess I can't resist, throwing in some more research and development efforts in here. On the ENL Speed Daemon, something that we used to tune ENLs, because this is the thing. Some wires and cables quote the speed of transmission of the electronic signal through various wire or various material, but they are very rough, so 70% the speed of light. But we're talking about the speed of light here. We need some decimal points. Now the length of an ENL's transmission line can change if you've got even thousandths or millionths of a fraction of the speed of light still plays into the speed of transmission and in the design of the ENL. So if you look at this problem the other way around, we can build an ENL that is an archetype ENL that can, when you connect it to a certain transmission line, it'll tell you what the electronic speed of transmission is. So this is something that I haven't seen in the market, something that tells you specifically the speed of transmission. What they do tell you is the delay time, and that's not always the same thing. It's not always the same thing. You get time instead of speed if you measure the length, but the length itself is the parameter that goes into designing the circuit. So that's been our catch-22 when designing ENLs also.
Are the current materials uniform enough?
I think that they're uniform enough. There's a rating when you produce the PCBs that give you a percent error in the height and the width of the thing, but it's very small. I think they do very well. What else do we want to do? This has been a question from a while back, whether or not what the ENL would do with a modulated signal. So this is a very ambitious effort to possibly use ENLs to replace the heterodyne receivers, which was that complicated graph that I showed about what happens with the signal when it comes in. It gets multiplexed and it's got all this craziness, and then it ends up with an analog to digital converter. It's hard, but probably not impossible to do. It wouldn't be just a single ENL, but it would be a circuit, around the ENL. That would be a pretty interesting thing to do and have a direct sort of value proposition, because once you build that, you have your own receiver block. So then you just need a microphone and a speaker, right? And then you've got a phone, because that's it. That's essentially the whole thing. So that would be interesting to do. Carrier frequency sniffer design. This was a neat idea. Yet another thing that we want to do with this is we were talking a lot about Wi-Fi and Wi-Fi channels, for instance. Well, if we had a 16-channel ENL here with the LEDs connected to the comparators that just spike whenever the frequency is there, we could just put it on the table and it would tell us what channels are being transmitted here. So this is also something that can be done with a computer. I know that there's some apps that do channel scanning and just tell you which channels are being populated by what, and they give you a lot more information. They tell you who's transmitting on what channel. But this could be like a dumb, quick trick tool, that you can just turn on and see exactly what it is, like a discontinuous. It's not connected to your phone and stuff like that. I could see network engineers finding this useful. Especially if you're moving around, a room and you're trying to find faults and stuff like that. Not very difficult to do. Transmit and receive test with a custom antenna design. This is an effort to pair a transmitter with a receiver ENL, and see if we can come up with a specific antenna design, because antennas can be patented. It doesn't that would be a nice way to sort of wrap the ENL into, you know, part of this transceiver receive block. And there's another couple of curious effects that I guess I discovered inadvertently, is that the ENL seems to act in a really interesting way when used in fiber optics. Again, only theoretically tested so far. I did do a real world test just to verify whether or not it's real. But if you add this is going to be a big parenthesis, you know, is if you add a blue frequency like 410 megahertz, 410 nanometers, with a yellow frequency, there's no color in the signal, right? It's just a signal traveling through. Well, what you get out is green. You're not supposed to in this kind of experiment. So the ENL prefers to act along the lines of the laws of physics than it does along the lines of electronic theory. So blue plus yellow gave me a green frequency. And I don't know where you can use this. It's kind of one of those fantastic.
Just like our eye does. Huh?
Just like our eye does, but I don't know. Like a whole other, you know, when everything else happens, Andreas can go and indulge. We mentioned briefly, you know, applications in space, especially with the terahertz or the megahertz. Sorry, the gigahertz ENLs are applicable to microwave frequencies, microwave technologies, which are mostly used in space. And because of the predominantly analog nature of the ENL, it's inherently radiation hard. So analog devices are inherently radiation hard because cosmic radiation, you know, affects digital signals. They flip bits from zeros to one. So we don't have that problem. So less shielding, less weight. You know, you can use them in space quicker, easier, cheaper, or charge an arm and a leg for making them for space. Now, Intel just produced one that's meant to be like a neural processor. It's not a neural processor though. It's digital. It's a digital processor, and we're like really. Gosh, what's the word? We're like really touchy about what's analog and what's digital in this area here. You know, we're like, no, it's not. That's not digital. It's not real time unless it's analog. It's like real time digital decoder. No. A real time analog decoder is what is really real time. That's not real time because you still have processing times inside there. You have windowing. We know what you're trying to do to get around the problems that you're having. And that's not the approach that we're taking. We're saying that there is a direct path to success, and that is by preserving the analog nature of the circuit, is the going back to basics and using the laws of physics in and of themselves, and using the results that we have. Okay, so now we've had intermittent but consistent funding. You know, we've had some funding come in every year. We've had you know, third-party validation. We've gone through a government grant, you know, or two. We've continued the research and development. You know, there've been various iterations, but it's been slow. It's been really slow, and it's because it's just been me basically, and like someone that we're contracting. It's not enough. It's not enough. So now you have everything. You have a novel innovation of a device that recognizes certain frequencies. This is the ENL. You have a patent. You have a system for stabilizing the output, which all analog systems have to have, linearity in their response. And you have an output mechanism. It's a component level innovation, you know, and it's part of a toolkit that an electronic engineer can use to refine their signals. Like I think that the easiest thing that you can do with an ENL is to build it into an antenna. Build it into an antenna. The first thing that comes out of the ENL is very similar to what a bandpass filter does right now, but build an ENL the first thing, you have a signal. Signal comes in. First thing that it should encounter is an ENL. Signal comes out. Last thing it should encounter is an ENL. Just cleans up all of the signals. Is there a specific frequency that you want? Yes. It's just an ENL. Right now, the result is what? Is there a specific frequency I want? Too bad, because you've got a flat bandpass here. You can't get the one frequency you want. With the ENL, you get the one frequency you want. Here, you get this group of frequencies in a traditional bandpass filter, and then you have to do a Fourier analysis. And all this craziness in order to find out exactly which frequencies you have. And then you still have mirror images in. But it's a product of the digital approach to signal analysis. It's a digital filter for an analog signal. There should be an analog filter for an analog signal. You can digitize it afterwards in order to produce a screen, right? The final stages. You can do whatever you want at the output. But while you're processing the signal, you try to keep it as intact as possible, preserve as much of the information as you want. And that was impossible so far because it produced too much noise and errors and things like that. But that was 50 years ago when we made the break from analog to digital technology. You know, those crystals, transistors, you know, they got hot. I mean, you kind of warm your hands.
The tubes?
The transistor tubes. You know, you could warm your. Yeah, they had heat up times and stuff like that. That's not the modern world anymore. That's not the modern world. We use the current digital findings as a principle, you know, to go back to this analog innovation and try to preserve this analog signals throughout the various components that we can make. So that's like a principle statement, like an ethical kind of statement for the company, that we believe that the future of information and technology is analog, and our technology is designed to incite this reversion back to the analog world, and realize that the places where it's used, you know, like where do you use a transducer, for instance, to convert a vibration to an electronic signal, you know, or when a machine is working at peak performance, when it hums, you know, what we understand subjectively. You know when your car's wrong.
Doesn't sound right, yeah.
You know when your car's wrong. There's no, you know, you sit in the car, oh, there's something wrong with this car. Oh, it drives, your buddy's saying, oh, it drives perfectly. You're like, no, there's something wrong with my car, man. I know my car. What does that mean? You've been absorbing these frequencies. You've been training yourself subconsciously. You know what they are, right? You know what they are. Well, what if you had a device that monitored the frequencies that came out of your engine in real time? And when they deviated from peak performance to something else, just turned red. It says you have a really noisy spectrum in these areas. That means something's wrong with your engine. Automatically, you can tell what this is. Now try to apply that to something like a bullet train, right, or a jet that has very specific tuning.
I'm thinking of like I did a lot of work with a group that tunes and does the turbines. Turbine seems like and that's a real big deal. You know, you have a turbine that is driving a power generator that's maybe running a oil platform or whatnot.
Mm-hmm.
It's a big deal if that goes down. It can cost a ton of money, you know, for even the slightest downtime.
Analog logic. That's another pet project is because of the way the ENL works, this was early research and whether or not a neural network, we could use ENLs to build neural networks, and the neural networks that are currently used are digital. This is another funny thing. It's a decision tree, right? So we're talking about a neural network closer or akin to a nervous system. You know, how you use an analog flow. So we still have kind of a binary output in that the frequency is either there or it's not, and the ENL would trigger if it is present. So what if you use this to populate a decision tree based on ENLs where you have some kind of frequency that you need to analyze? So let me give you an example. Decryption. Okay? There's logical steps. If you knew what steps you needed to take, an ENL bank would do this at the speed of transmission of the electronics. So it would do it at infinite speed, at the speed of light. The signal would come in, it would move through the channels, the output would come out. You wouldn't be trying to, there would be no brute force approach needed for decryption. Okay, so this would be awesome. So you would have one closet that decrypts certain types of signals with 10,000 ENLs. Let's give an example, right? It doesn't matter how big it is. Who cares how big it is? It wouldn't be bigger than a cray, you know, I'll tell you that. Another thing is, you know, certain logical operations, we mean building a set of mathematical calculations. So if you build mathematical calculations using ENLs, the consequence of this is that you can start replacing digital signal processors with analog signal processors. Okay, so instead of doing fast Fourier transforms, you could do direct frequency composition, direct frequency component decomposition, which is the commensurate of what the ENL does. So now you've replaced the DSP with an analog device. The speed is instantaneous. There's no heat when it grinds and stuff like that. Then you go to the next step. You build a more complicated computer, right? You make mathematical processing unit, for instance. You know, carrying the one and things like that. You know, you can do stuff like that with the ENL. Only instead of a binary or digital system, now you have, and it's not even a trinary system or other things that people are trying to get around. You have to reimagine how you're going to do the math, but you're not restricted to ones and zeros, because you have a zero, the presence of a zero. You have a Boolean, this operation is complete versus it's not complete by the effect of the ENL itself, the ENL triggered, which means that the frequency is present. And then, once the frequency is present, the information that's carried is the inherent signal that exists within the ENL. So I can imagine really complicated mathematical computations being performed by networks of ENLs in this way. So I have a couple of like adding and subtracting, for instance, models in simulations and SPICE simulations. So if you can add an analog, for instance, what would it look like? If you can subtract, that add in an analog is what that blue plus yellow gives me yellow, gives me green came up. I was like, didn't expect that, but it's pretty awesome, you know. I have things like subtracting, so subtracting frequencies. So it's like, what if I subtract 1 by 1? I should get 0. That's basic mathematical theory, means the presence of a unity, the presence of a 0, the presence of an inverse. There's certain basic levels that you can build mathematical theories over. It's called group theory. So if you subtract a frequency from another frequency, then you've got a notch filter. So I already have that. Right? You can band reject or notch. You can subtract the filter. You can subtract the frequency. So you actually have the basis of a mathematical language that would operate in analog terms using ENLs. And again, there is no describing where this could go. And that's a good way to end this.